Alright, so for today's pre-lecture video, I wanted to do a short example that employs both refraction, so we're using Snell's Law, and also the idea of total internal reflection. So we learn about Snell's Law and how light will bend as it travels from one material into another. There's an interesting phenomena that occurs when we go from a region of higher index of refraction to a region of lower index of refraction. If you remember, according to Snell's Law, if a light beam is traveling in an area of higher index of refraction, when it passes into an area of lower index of refraction, it will bend away from the normal, so that this angle, the angle of refraction, is bigger than the angle of incidence, which is shown right here. So what happens then, as we might expect, is as our angle of incidence grows, of course, so will the angle of refraction. And you get to a situation where, I'm going to show it on a separate piece, a separate drawing, where at a particular angle, which we call the critical angle, the angle of refraction will actually be 90 degrees. And so we're going to call this N low, and this is N high. The idea being that if we ended up with a higher angle of incidence here, in this higher index of refraction, what would happen is the light actually wouldn't pass into the new medium, but would obey the law of reflection and just reflect back into the material. It would reflect off of the interface between the two materials. And this is what we call total internal reflection. Mathematically, we can find the critical angle by using Snell's Law and using the fact that our angle of refraction is 90 degrees. So we would say N high times the sine of the critical angle is equal to N low times the sine of 90 degrees. And so you can actually solve this for the sine of the critical angle. And because the sine of 90 degrees is just equal to 1, it actually is the ratio. The sine of the critical angle is the ratio of the two index of refractions. And then we can just use the inverse sine to figure out what that critical angle is. I like to always start with Snell's Law to solve for the critical angle, so that I don't have to try to solve or remember another special equation that gives me the critical angle, like this one right here. This is just Snell's Law, and if I understand total internal reflection, I can remember that this angle should be 90, and I can actually then solve it pretty easily. So, what I do is look at an example where we're using the idea of total internal reflection, or the critical angle, and then also do a problem with a prism, because that's something that we run into, a type of problem that we do. So right here we have a light beam coming into one side of the prism. It's refracted, so it does bend, and it's refracted to an angle of 40 degrees. And we're told that over here on the far side, that this angle right here is the critical angle. And so we need to try to figure out what, what is that angle, or do we need to figure out what the index of refraction is of this glass? We don't know either one of those. Now, one of the things that we can do when we have these prisms is we are going to be able to make a triangle. So right here we see that this is a triangle, and we're going to use that to help us figure out some of these unknown angles. So the triangle here that's sort of traced in the pink, I know that all the angles in this triangle add up to be 180 degrees. And I also know that this angle right here and this angle, the 40 degrees, add up to be 90. So knowing that the 40 degrees plus this angle add up to be 90, I know that this is 50 degrees. And then I know 50 plus 90 plus this angle have to add up to be 180. So 90 plus 50 is 140. So that means that this angle has to be 40 degrees. And that actually allows me to find the critical angle. I didn't even have to do a calculation. I can just solve for it. It's 50 degrees. And so that is going to allow me to solve for the index of refraction. So I'm going to find n for the glass. And the way that I'll do that is I'll say n for the glass times the sine of 50 degrees is equal to n for the air times the sine of 90. Because remember, because what the problem told us is the 50 degrees is actually the critical angle. So now I can solve for n of the glass, which is going to be n of the air times the sine of 90 over the sine of 50. So we're going to say that n of air is 1, because it basically usually is about 1, or 1 in a very small fraction. Sine of 90 is 1, and then divided by the sine of 50. And this gives us an index of refraction of the glass of 1.3. Now we can go back to the incident side, and so when on the opposite side over here, we can say that n of the air times the sine of theta A, which is what we're looking for, is equal to n of the glass times the sine of 40 degrees, which is the refracted angle at the first interface. So the sine of theta A is equal to n of the glass times the sine of 40 over n of the air. We know the index of refraction of the glass is 1.3 times the sine of 40 over 1. And so we actually then can solve for the angle A and find out that it's 56.7 degrees. And that is it. So that's an example kind of rolling up all together. Snell's Law, critical angle, and also working with prisms.